Alright, so we're talking about the hardness. Guys, just focus, please. We're talking about the hardness. It's not how hard the mineral is and how much damage it can handle being thrown up against the wall. Good guess. Yeah. That was a good guess. But really what we're talking about is the resistance to scratching. This is by far the most reliable test. And so when we look at minerals, that resistance to scratch, that's the hardness, how well it resists scratching. Basically, that is all determined by the arrangement of the mineral's atoms. And guys, this is so important. I think I keep telling you guys this, and I'm still not sure you guys are really listening to me fully. A lot of what we see on a grand scale and the interactions that are taking place on a grand scale really boil down to the behavior at the atomic and molecular level. And I cannot stress that enough. What's really happening on our level where we start and we're observing what's going on, it's really because of an interaction going on all the way down at that minute scale, all about the atoms and the molecules. And if those atoms are tightly bonded, it's very difficult to scratch that surface because a scratch is literally undoing bonds. And so when we look at that, that's really when we talk about the hardness. And this is all developed by a guy named Friedrich Moe. Again, a German geologist. Remember, the top nation in the world for geology during the middle of the 19th century was Germany. Okay, so we get Friedrich Moe. And he comes, and this is why it's often called the Mohs hardness scale. No, we're not talking about Mohs, who's got the local tavern. Those guys are Simpsons fans. So when we look at this, the scale is basically 1 to 10. With talc being the softest of all the minerals, and diamond is basically the hardest. So that's your scale. Now, what we have over here is a comparison, some basic things to understand. So, find your talc or your gypsum, the feldspar gypsum. Okay, that's the pink one. Find those in your mineral kits. And take your thumbnail, and you can actually scratch the surface of that mineral.
It's not.
So again, if we look at the hardness of a human's fingernail, the hardness is only 2.5, which means that the fingernail can scratch anything with a hardness lower than that. So that means anything with 2.5 or lower can be scratched by the fingernail. If you have a copper penny, which don't really exist anymore, copper penny has a hardness of 3.5. If you look at the glass, this is why you guys have the glass plates in your kits. The glass plate has a hardness of 5.5. So what we can do is like, okay, I'm not really sure if it's this mineral or this mineral. Well, take a look at fluorite. What's the hardness of fluorite on the scale? 4. So is fluorite going to scratch glass?
No.
Oh, try it. Take your fluorite mineral and try to scratch your glass.
No.
Fluorite is
I'm tired of doing everything. I look for the big standards and what? I need to like grab.
So the fluorite will not scratch glass. Guys, come on, stay with me, please. However, if you take quartz, find your quartz sample, and the quartz will scratch the glass because quartz has a hardness of 7. And then what some geologists do when they have their field tests, they have these kits that they take out in the field. And then they have these things. They're kind of neat. And they're tips with the different minerals. So when I look at this, this is number 6. which is probably going to be, well, sure, probably, I thought that was topaz. No, it might be fluorite. But again, you can see where they tip these with the different types of minerals, and then it kind of tells us the hardness. Now look here at number 9, and it's a ruby tip. See the red ruby, that's corundum. That's what's being passed around right now is the red rubies. And then over here I have the 8.5, which is going to be probably topaz. So again, so these are things that geologists use out in the field to help them identify different minerals and different rocks that are out there. So what I want you guys to do is there should be a paper that is with your set. If there isn't, I want you to work with a group that has it.
We don't have one. No.
And I want you guys to write down the hardness for your minerals.
Alright. Let's just do it.
So is it just less than or greater than 5 tons?
No.
Skip.
Alright guys, so the next thing we need to talk about is cleavage versus fracture. And guys, all cleavage is when the rock breaks along even planes. When you look in your mineral sets, perfect example, rock that has cleavage is calcite. And a lot of times when we look at the cleavage of minerals, what we're looking for is the number of planes on which it cleaves. So for example, if you look at your mica sample, mica and biotite. Biotite is this thin flaky stuff. It cleaves in one direction, that horizontal direction. So it's what we call a single direction cleavage. However, if you look at calcite, calcite is going to cleave in 3 dimensions. So you have the horizontal, the vertical, and then the depth. So it cleaves in all 3 directions. So this will be what we call perfect cleavage. Now, fracture is exactly, what does it mean to fracture your bone?
Crack it.
Crack it, right? And if you fracture, you crack it, it's not going to break evenly, is it? Okay, so that's what we call fracture. It's when we have jagged edges. So it's when we break along uneven planes. Perfect example of fracture is quartz and labradorite, and that's something you guys have already seen before as well. They're kind of jagged edges, not real smooth. Now occasionally we can have special types of fracture, especially when we get into rocks. When we look at something like obsidian, and obsidian can have this thing called a conchoidal fracture. And what that looks like is basically it's going to be fan-shaped. And what you have are these radiating arcs that come off from the point at which it's breaking. That's called a conchoidal fracture. When you have this fan-shaped break to it. So, do me a favor, go back through your minerals, figure out whether that mineral cleaves or if it fractures. Alright, the last part we want to talk about today is density. And